Hi everyone. In this video we'll begin our study of a field of math called graph theory. Now this type of graphing may have nothing to do with the types of graphs you've studied before. There are no coordinates like x and y. There's no graph paper. We don't need rulers to draw the graphs. So it's actually quite different. So let's begin with a discussion of what graph theory actually is, and then we'll go into some basic concepts and vocabulary needed to study this type of math. What's interesting about graph theory is that it is a historical topic. It can be traced back to a single question from the 1700s, but then it also has modern applications today, and there's quite a bit of current research in this field. It's by no means a dead field. So let's talk first about its origins. Back in the 1700s, there was a town in Prussia. It's now in Russia. It was Königsberg, and the citizens in Königsberg liked to take walks in the evenings, and their city had this river that went through it, and they had 7 bridges over the river. So one of their favorite pastimes was to try to find a route that would cross all 7 bridges exactly once and begin and end at the same location so that they could get home or back to wherever it was they started. So they tried for a while and they weren't able to find such a route, but they weren't sure if they were just missing one or if it was actually impossible. So they contacted the Swiss mathematician Leonhard Euler, who lived fairly close by, and they asked if he could prove whether or not such a route was possible. So he was quickly able to solve this problem. He thought it was trivial, but what he thought was interesting was that it didn't really fit into any of the current branches of math that existed at the time. So he started studying it, and that's how the field of graph theory began. So this is a famous problem, and you'll actually be able to answer this for yourself by the time you get through a few more videos. So we'll leave that one be for now. And then I wanted to mention one other one. The more of a modern application would be a type of problem that involves traveling between different routes and between different destinations, finding different routes, and seeing if you can find the most optimal route. So we'll discuss what that means. What does it mean to be an optimal route? But here's one person's answer. And if you view the PowerPoint that goes along with this video, there's a link here to an article. And somebody actually came up with an optimal U.S. road trip that hits all 48 connected states. And it doesn't stop. It doesn't travel unnecessary distances, but you are able to most efficiently hit all 48 states without covering too much distance. The destinations along this trip are all U.S. landmarks and historical monuments if you're interested in that kind of thing. And the person who did this based it on Google Maps and also a Python script that he wrote. So some of these graph theory questions we can now answer with the help of technology. So you're not having to back up and do this by hand as they may have done in the 1700s, but it is interesting that things like GPS and maps that we use today are based on graph theory concepts, and we also are researching new ways to use graph theory, so a good understanding of some of these traditional techniques and historical problems is useful in being able to create and answer your own questions in the future. Okay, so that's an introduction to graph theory, just the origins of that field of math and what it could be used for. We'll look at some more examples in the next few videos, but what I'd like to do now is discuss some of the vocabulary in this section. So first of all, what is a graph? We've talked about what it's not. No graph paper, no x and y coordinates. Right, but what it is, a graph consists of a finite set of points called vertices, or singular vertex, and line segments or curves called edges connecting the points. So that's it, vertices and edges. We're not real concerned with plotting vertices accurately. We can, really place them anywhere that's convenient. Size doesn't really matter, so you can make a small vertex or a really large one, and the idea is still the same. And then edges, we're not really concerned whether or not they're straight, so you can do a straight edge, but you can also do a curvy edge as well. So here's an example. This is a graph. Okay, it's got some vertices, some edges. It also has a special type of edge, a loop. This is an edge that begins and ends at the same vertex. Alright, so if we go through and name the vertices, right, vertices get named with capital letters. So the vertices in this graph would be A, B, C, and D. Okay, pretty easy. Edges get named similar to how we would name them in geometry. We list the first and last vertices, so kind of like the endpoints of those edges. Alright, so for this edge, I could talk about edge AB. Now in geometry, we would normally put a line segment symbol over that to show that it's an edge, but in graph theory we don't. Okay, so AB means the edge AB. Alright, what else? What other edges do we have? So let's try to list them all. Okay, I've got BC. Alright, I have CD. Okay, I have DA. And also, like in geometry, it doesn't matter if you call this DA or AD, so you can reverse the letters and it would mean the same thing. Okay, we have AC and BD. And then what do we do about the loop? Well, your textbook doesn't really discuss this, so for our purposes, let's call this either loop C, okay, or if you wanted to just say CC, then that would sort of convey the same idea as well, that you're starting at C and ending at C. Okay, so then which vertex has a loop? I think we've answered this question as well. Vertex C has a loop. One of the other things we can do with graph theory is take maps and redraw them in a simpler way, just to focus on the key features. So if we're interested mostly in connections between different things, then we can sort of get rid of some of the unnecessary detail for studying a problem. So if I wanted to translate this map of some islands and bridges into a graph, maybe I'm not really concerned with all of these curves to the islands, and maybe I don't care how wide the bridges are. I just care which islands are connected with bridges. Alright, so let's translate this, and you can choose whether or not you want the bridges or the islands to be the vertices. So I think in this case it kind of makes sense to do islands as vertices and then the bridges as the edges. But depending on the problem, sometimes we will reverse that. Okay, so we've got Alfalfa Key, and you may have seen already they've conveniently named these islands for you with letters in alphabetical order. All right, so we can label these, with capital letters that make sense. All right, so we'll call Alfalfa Key A, and then we've got Blackbeard K. We've got Canary Island and Duck Island. And I'm going to put this one over here. You don't even have to really be accurate about where the vertices are, all right, as long as you get the right connections. All right, so Alfalfa Key is connected to all three other islands. So I'm going to show that by using edges to connect those vertices. And notice again the connection between A and D doesn't really look like the one on our map, but that's okay. Okay, Canary Island is connected to all three. And so is Blackbeard K. Okay, so they're all connected to each other. Alright, so there's one example of a graph. Here's another one. This is a floor plan of a house. Okay, and we need to decide what's important here to represent in the graph. So maybe we want to do rooms or regions and then show which are connected using a doorway. All right, so we've got 4 regions inside the house. We've got the living room, dining room, kitchen, and bath. And I'll choose capital letters that correspond to those. And then we also have this outside region, so I'll put a vertex for that and call that O. Okay, so what's connected to what? Well, the living room, I see a doorway into the dining room, the kitchen, and also the outside. Okay, so I've got edges to show that. Then let's see, we'll go on to the dining room. All right, we've already connected that to the living room. It's also connected to the kitchen and the bath. All right, and then the bath isn't connected to anything else other than the dining room. Kitchen has one more doorway to the outside, so I need to connect the kitchen and the outside. Okay, and then that should finish it, so let me just double check. The outside here, that's connected to the living room, and I've already connected it to the kitchen. Okay, so that takes care of all the different regions. Here's another example. This is a map of 5 counties in central Pennsylvania. Draw a graph that shows the counties that share a common border. Let the vertices represent the counties, and the edges represent the common borders. Okay, so we don't have a choice here. We're given the vertices and the edges. All right, so we'll do vertices for the counties. So we've got V for Venango, F for Forest, E for Elk, C for Clarion, and J for Jefferson. And then connect the ones that share a common border, meaning they touch each other on the graph. Okay, so Venango shares a common border with Forest and also with Clarion. Okay, so that one's done. Forest also connects to Clarion and Jefferson and Elk. Okay. Elk also connects to Jefferson. And Jefferson also connects to Clarion. And Clarion, I've already done the 3 borders with the counties adjacent to that one. Okay, so that is a graph that represents this map. Okay, and then one more. We have a plan of streets in a neighborhood. And we can draw a graph for this neighborhood, use the intersections of streets as vertices, and the streets as the edges. Okay, so here we have to decide what to call these vertices, because we're not actually using the labeled streets as the vertices. We're using the intersections, which aren't labeled. All right, so one option is to give them a capital letter name. Okay, that makes sense. Based on the streets that intersect them. But what your textbook does for this is just leave the vertices unlabeled. So it does depend on the question. We'll try to stick with ones mostly that are labeled, but sometimes we're just concerned with seeing a quick graph and we don't need labels for everything. All right, so that is an option as well. So this one I'm just going to quickly do because I think I think this is pretty easy. The graph's going to look almost the same as this map. All right, so every time we have an intersection of 2 streets, we've got vertices here. Okay, Iris hits Marigold, Iris hits Rose. Okay, so I end up with all of these vertices. Alright, and then the streets are the edges, so I'm just going to draw in all of those connections. Okay, and there's my other 2 streets. Okay, now just to be a little bit different here and emphasize the fact that you don't have to draw things. I've got 2 more. Okay, you don't have to draw things exactly like the picture. So if for that last edge, if I'd wanted to, do something like this, All right, that's fine. Okay, and that's an accurate graph. One other thing to mention, be careful where you see vertices labeled or clearly marked. So in this case, like notice at this spot, even though these two edges cross each other, there's no vertex there. So those edges don't actually touch at that spot. You can think of this kind of like a bridge or an overpass and a road going below. Okay, they sort of look like they're crossing from the top view, but then if you look from the side, they're not. Okay, equivalent graphs. Right, so we've already touched on this idea. You can draw two graphs that don't look quite the same, but they are technically still the same graph. Right, so we define equivalent graphs as graphs that have the same vertices connected in the same way. So if you see in this diagram, a quick glance shows us that the vertices are the same. Both graphs have A, B, C, and D. But then we need to check that all of the edges also match. That's what we mean by vertices connected in the same way. Okay, so I see A on the left here is connected to B, C, and D. And on the right, A is also connected to B, C, and D. Okay, B is connected to all three other vertices, and it is on the right as well. Okay, C is connected to all three, and it is here as well. And same thing for D. Okay, connected to all three other vertices. So these are equivalent graphs. All right, how about this one? A quick glance shows that both graphs have A, B, C, D, and E. All right, so now we're looking to see if all of the edges match. And you can look at this one for a couple minutes, and eventually you might notice that these are not quite the same. In particular, this graph on the left has an edge connecting B and E, and this graph on the right has no direct connection, no edge directly from B to E. So these graphs are not equivalent. All right, so that answers a couple questions for us. We know how graph theory started, we know what a graph is, and we should know how to convert some actual maps or floor plans into graphs.